In this work, we consider the problem of testing the goodness of fit of a sample of items from many categories to the uniform distribution over these categories. This problem is sometimes called uniformity testing or identity testing against uniformity. The main result of this work are asymptotic characterization of the minimax risk and also the minimax test under missing ball alternatives when the tests are restricted to the histogram of the sample. Hopefully, I will convince you that this characterization provides a significant contribution in understanding this fundamental and relatively well-studied problem. So let's begin with describing the problem. Here we have a sample of lowercase n of items from capital N categories. And we focus on the so-called high-dimensional situation in which the number of categories is perhaps larger or equivalent to the size of the sample. Okay, so the size of the sample is at most linear in the number of categories. Now here you can replace the term categories with alphabet or perhaps dictionary, and accordingly, if instead of sampling items from many categories, you will sample words from a dictionary or letter from an alphabet. We define here the random variable OI as the number of items observed from category I. And our goal is to distinguish between two hypotheses. The null hypothesis stating that counts from all categories obey the same Poisson distribution. And here we control the rate of the Poisson distribution using what we call the uniform rate sequence U, in which each coordinate is 1 over capital N. Okay, so overall, under the null, all categories occur with the same frequency. So this is uniform distribution. The alternative states that observations of the items from the categories obey a different rate vector, Q, which is taken from an alternative set of rate vectors, which necessarily does not contain the uniform sequence U. We will do in this work, we will define the alternative set by the removal of an LP ball around the uniform rate sequence U. Many times the case P equals 1 is considered in literature because it's relation to the total variation distance when the alternative sequence is also a probability distribution. However, our analysis can handle the case larger than 0 until less than or equal to 2. This figure conceptually shows the situation for the case when the number of categories is 2. Okay, so capital N equals 2 in this case. Now, we are interested in a minimax analysis. What does it mean? First, let's assume that we have a particular test psi. So our test maps the sample either to 0 between the null or 1 the alternative. The risk of the test is defined in the standard manner as the sum of type 1 plus type 2 errors. And the minimax risk corresponds to the best estimator the statistician can play under the worst choice of nature from the alternative set. The problem that I just described is quite general, and there is a remarkable long list of related earlier studies of the problem that it is impossible to put here. I just want to mention two very fruitful lines of work that appears to be the most relevant. So the first line of works deal with the problem of detecting a signal in white Gaussian noise. This line of work is most identified with Inkster and his collaborator. And using the same technique as in signal detection, Inkster also characterized the minimax risk for goodness of fit testing against uniform distribution, but only when the alternative set has some smoothness condition or uniform boundness condition on its members. In contrast, in our setting, we do not assume such conditions, and indeed, we show that the minimax risk behave differently than in Inkster's case. The other line of works is the one identified with the literature on property testing in theoretical computer science, which also did not assume the kind of smoothness that I just mentioned. Now, goodness of fit testing in the property testing literature is one of the core problems, and we will discuss later on how these results are related to ours, or in other words, how our result generalizes those earlier works. So in our case, we are focusing on what we call the histogram of the sample. Okay, so instead of looking at the sample from here on the left, we're looking at a different representation of the counts by what is shown here on the right. We reduce attention to this histogram. By histogram, I mean a summarization of the samples based on how many categories we have seen for a specific number of times determined by the histogram ordinate. Okay, so for example, x0 here is the number of missing categories. x1 is the number of singletons in the samples. x2, the number of collisions or coincidences, and so forth. Okay, so we'll define xm is the m histogram ordinate, m running from 0 till infinity, but eventually it is bounded by, for m equal n, we will guarantee to have m equal n plus 1, we guarantee to have 0. In addition, we also reduce attention to test that statistic that are linear functionals of this histogram ordinates. Okay, so each test is characterized by this vector of weights w, which we also denote as the kernel of the test. Okay, so here are examples of two popular tests and their kernels. First one is the chi-square test, and the second one is the collision-based test. Collision-based test, it just simply counts how many categories we've seen at least two items or more from those categories. So as you can see from these examples, the restriction above about the test based on the histogram is not necessarily reduced to generality of our results, because most popular tests actually abide by these restrictions. Okay, so with that, let me summarize the results of this work. The results are given in an asymptotic setting in which the number of samples and the number of categories go to infinity, but the number of samples is at most linear in the number of categories, and also potentially much smaller, which also cover the sublinear regime. So we also assume here that epsilon goes to 0, although this condition can be relaxed in some situation, and this for the details you need to see the paper. Now the first result, number 1, pins down the minimax risk simply by this limit. Okay, here phi is the standard normal cumulative distribution function, CDF. The second result, essentially derived from the first one, it characterized the kernel of the minimax test. Now, before I turn to discuss the significance of the result, let's first see that this asymptotic, the characterization is useful in the sense that with finite samples, we really get something that's getting close to this expression that you see here at the denominator of this limit. This figure tells you that this is indeed the case. Here you can see in dashed lines the asymptotic predictions from our expressions, and in continuous lines you can see the empirical risk obtained from simulations with finite sample case. The main takeaway for the different colors correspond to different ratio of number of sample size compared to the number of categories. Okay, so the blue one, for example, very small sample size. The red one, sample size is twice the number of categories. The takeaway from this figure is that it seems that our expression for the minimax risk provides a good approximation for a finite sample situation. Okay, another slide shows the fact that the minimax test is indeed superior to other proposed tests. So in this figure, we compare the risk under the minimax test to the risk of the chi-square test and also the collision-based test. And what you see here is the ratio of each of the tests to the minimax, to the theoretical minimax risk. Okay, so the continuous curve is again the empirical one. The dashed one is the theoretical one derived from our analysis. And for example, in this case, you can see that for the chi-square test, for epsilon between about 0.23, the risk of the chi-square test is about 50% higher than the risk of the Minimax test. And the collision-based test has a risk which is better than the risk of the chi-square test, but still higher than the risk of the Minimax test. On the right-hand side, we present the case where lambda equals 0.5. So number of samples is about 50% of the number of categories. Here, the chi-square test and the collision-based test perhaps change places in which one is better, but both are still dominated by the Minimax test. Okay, so this slide explains the significance of the result, perhaps in a slightly larger context compared to earlier works. We will assume here that p equals 1. It is just to simplify the expression, but the same conclusion actually holds for all cases of p that we consider, so meaning p is smaller or equal to 2. Our characterization, the Minimax test, is essentially the characterization of this function of the parameter of the problem that describes the asymptotic behavior of the Minimax risk. Now, previously, a very fruitful line of research, especially in theoretical computer science, showed that if this term n epsilon square over square root of n goes to infinity, then the Minimax risk vanishes. And in the other case, if n epsilon square over square root of n goes to 0, then the Minimax risk goes to 1. In other words, all tests will be trivial in the Minimax sense if this is holds. Okay, so this is some kind of a phase transition for the Minimax risk that was derived in many works, and it was shown that several estimators actually satisfy this phase transition. Now, the problem is that we don't know what happened on the boundary condition. In particular, we don't know how to compare two testers that achieve this phase transition. In this context, it is worth mentioning a recent work by Gupta and Price that proposed a sharper estimate to the Minimax risk under some assumption of the variance of the alternative set. Their estimate also followed from ours. Until this work, we ended up with many tests that are perhaps optimal with respect to the phase transition, but it was unclear which one is better and why. And this is where our characterization really becomes useful, because it allows the comparison of estimators at a constant level rather than only at the rates. Okay, the situation is perhaps analogous to the contribution of Pinsker to the literature on non-parametric smooth function estimation, or if you want to go farther down history, the analogous to the notion of Fisher optimality of estimators in parametric setting. Okay, so same as here, when you have the exact asymptotic behavior, you can discuss the efficiency of inference procedure compared to the constant, and then really understand what properties of your test are important. Okay, so for example, what do I mean by an understanding of what are the properties that are important? On the top left are the weights of the Minimax test. Okay, so this is for different value of lambda. Lambda here represents the ratio of the number of samples to the number of categories. Okay, so the blue here corresponds to a very small sample. Okay, maybe perhaps what we just think about as the sublinear situation. Now, the first column here corresponds to the weight that we give to the missing categories, the second column to the singleton, third columns to the collision, and so forth. On the top right, what you see is the expected difference in the mean of every histogram ordinate under the least favorable prior that yields the Minimax risk, which we also characterize as a byproduct of the analysis. Now, the product of the weight times the expected mean for each histogram ordinate gives you what you see at the bottom here, okay, what we call the effective discrimination. Now, one notable thing from this figure is that for the case of a very small sample represented by, again, the blue bars, the contribution that gives you the effective discrimination is entirely from the collision statistic. Okay, so this is the case where the sample is small. Of course, when the sample gets larger, the situation changes dramatically, and collision may no longer a useful statistic to rely on. Before concluding, I'd like to mention something about the proof. The proof itself involves several steps that I will not get into the details due to interest of time, but I just want to mention two main ideas here. The first main idea is the transformation, the Minimax analysis to a Bayesian setting. Instead of looking at the alternative set, we consider a set of priors that on average realize the sequences that are within the alternative set. The second major idea is the adaptation of techniques from Inkster and Suslina. They discuss the Gaussian signal detection, but what we are looking at is a Poisson signal, and the adaptation here requires some work. All right, so now let's summarize. And in this talk, there are two takeaways. First, we have an asymptotic characterization of the minimax risk for testing the goodness of fit to the uniform distribution based on a histogram and linear test. The second is that significance of this result moves the discussion from rate optimality to constant optimality.